Hey Chem 20s, it's me, Mr. Jukely again. Today we are talking about stoichiometry and quantitative analysis. This is page 6 of our Stoich workbook. So if you're not already there, you probably want to open it up to page 6. And yeah, quantitative analysis, talking about all the quantities that we're dealing with here. So numbers and calculations. You also want probably your data booklet and a calculator to go through. So first thing that we want to go through and talk about is mole ratios. Now, I'm going to tell you right off the bat with this, you've already had some practice with this. You've already done most of the work for this section. It's just looking at it in a little bit more detail. So mole ratios, it's the ratio between the moles of any two elements, ions, compounds, etc. in a chemical reaction. That's pretty much what it says right here. So we're given this chemical reaction. So that looks like propane reacts with oxygen, produces carbon dioxide and water. Very, very, very nice. It's the ratio, it's those coefficients or those numbers in front that are really, really important for us. And remember, if there is no number in front, it's a number 1, right? We just don't show that number 1 very often. So what this is saying is 1 propane reacts with 5 oxygens to produce 3 carbon dioxides and 4 waters. Now we could talk about individual compounds for this, or we could extend that to the number of moles. And that's typically what we do for stoichiometry, is you talk about this in terms of the moles. So 1 mole of propane reacts with 5 moles of oxygen. So let's just check out the ratios real quick here. So the ratio of, let's see, we've got propane to carbon dioxide. So it's 1 propane for every 3 carbon dioxide. So that's a 1 to 3 mole ratio. That's not bad. The ratio of oxygen to carbon dioxide. So oxygen, let's see, I got 5 moles of oxygen for every 3 moles of carbon dioxide. So every 5 moles of oxygen that reacts produces 3 moles of carbon dioxide. Cool, so it's not so bad. We can use these mole ratios and then the idea that things react in these simple whole number ratios to actually figure out another compound, right? And figure out things about another compound. So for the sake of space, I'm going to cross off the middle one, B here, and we'll just look at A and C. So we're using that same chemical reaction that's right up top here, same chemical reaction. It says now if 0.55 moles of propane reacted in the above reaction, how many moles of the following would be produced? So we're looking at carbon dioxide. So I'm going to start with 0.55 moles, and I'm not going to be lazy here. I'm going to put C3H8 because that's what we're starting with, 0.55 moles of C3H8. Now I'm going to multiply this by a ratio, and in that ratio I want to get rid of moles of C3H8, and I want to end up with moles of carbon dioxide. So moles of CO2. Now it's a little bit tedious writing this out, but you can absolutely do it. It's no problem. So now all I got to go through is look at, okay, so I got a 1 in front of my propane. So it's 1 mole of C3H8, and I'm looking for carbon dioxide. Carbon dioxide is over here, so a 3 mole in front of the moles of carbon dioxide. In other words, 1 mole of propane produces 3 moles of carbon dioxide. And now look what happens with my units. Things on top cancel with things on bottom. Remember, if you want to put this over a placeholder, that's fine. And we go ahead and we can plug this into our calculators. So let's just get out the old calculator. I don't know what that was, but 0.55 times 3. Do we really need to divide it by 1? Not really, so that is 1.65 moles of, what were we looking at there? Carbon dioxide of CO2. Nice. Let's just try out one more just because, and then we'll probably skip the second example because it's kind of more of the same stuff. So I've got, actually, you know what? I just had an idea. Let's just forget about this. Let's just look at the next example. So now I've got 1.25 moles of water. Cool. 1.25 moles of water. Still the same reaction from way up top there. And we want to figure out how much carbon dioxide goes along with that. So I need to cancel out moles of CO2, and I need to end up with, oh, sorry, hold the phone, hold the phone. We're looking for moles of CO2. So I want to have moles of CO2 on the top, and I want to cancel my moles of H2O. So that's going to cancel, and that's going to cancel. Now I just have to go up. I'm looking at the mole ratio between carbon dioxide and water. So back to the original formula way up top here. So carbon dioxide, there's 3 carbon dioxides for every 4 waters produced. So 3 goes with the carbon dioxide, 4 goes with the water. That's no problem. Let's get out the old calculator again. So 1.25 times 3 divided by 4, that's going to give me 0.9375. 0.9375. I think we could do a little bit better with sig digs. So from the original up here, we've got 3 sig digs. So I might even round this to 938 so that I've still got 3 sig digs. And that's, of course, going to be moles of carbon dioxide. Very, very nice. So all the rest of the examples, and you can feel free to try out the rest of these examples here too. All they're really saying is, if we know one piece of information from one of the reactants, one of the products, doesn't matter what, we can figure out every other piece. So in this case, the first example, we knew the moles of propane, and we could figure out the moles of carbon dioxide. We did figure out the moles of carbon dioxide. We could have figured out the moles of oxygen. We could have figured out the moles of water. The second example, we were given the moles of water, so that's a product in this case, and we figured out the moles of the other product. We could have also figured out the moles of the reactants as well. All we need to do is cancel the moles of the thing we want to get rid of, have the moles of the thing that we're looking for typically on top, and we should be good to go, right? It's just canceling units like we've done before. So that's one big piece of this. So, stoichiometric calculations. This is a method of predicting reactants or products, kind of like we just did, based on the quantity of another reactant or product. Also, kind of what we just did. The big difference is now we're going to start to look at gravimetric stoichiometry, and gravimetric stoichiometry is all about mass, right? So if I'm given the mass of one thing, can I find the mass of another thing? Absolutely we can. It's a couple more steps, but we definitely can. So gravimetric stoichiometry always follows the same kind of steps. We want to, step 1, write a balanced chemical reaction, include all the states, all the balancing. It's everything that we've done before. One thing that a lot of people find helpful is underneath the reaction, write down everything that you know. Right? So all of the information that's given to you. We'll see, we might be a little bit tight for space for that in some of our examples and some of our problems here, but write it down or at least make a little note of it, right? Somewhere on your page. Writing it directly underneath often keeps it nice and clear. Okay, your second step is you're going to be given the mass of something, right? It's going to be our given sum, so we're given the mass of something, and we can use that mass and we can convert it into moles. Right? Do you remember how to do that? Molar mass is our thing. Molar mass. So we'll probably also have to calculate molar mass, but molar mass helps us convert to mass in moles. Step 3 is what we were just doing. We use our mole ratio to figure out the moles of something else, right? So the required substance, the thing that we're looking for. And then step 4, we use the molar mass of the next substance in order to figure out the mass of whatever required to find the mass of. That's a lot. Let's recap. Step 1, balanced chemical equation. Step 2, convert mass to moles. So let me just write that out a little bit nicer here. Step 2, mass goes into moles. Step 3, we've got moles of what we're given going into moles of what we're looking for. And then finally, step 4, we're going from moles of what we're looking for into mass of what we're looking for. Nice. Please include significant digits. That's one thing that's of note there. So let's check out a couple examples. There's a lot of examples and there's even more practice. So we'll probably only do a couple of these just for the sake of time. But yeah, we can do this. So the following questions, blah, 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 calculations, yada, yada, yada. Okay, let's jump into it. Number 1, ethane. That's C2H6 reacts with oxygen in a hydrocarbon combustion reaction. Part A, write the balanced chemical equation. Nice. So I've got C2H6. That's a gas. It's going to react with oxygen, so that's O2, also a gas. And it's going to produce, well, just like every hydrocarbon combustion, carbon dioxide gas and water that's, a gas. Everything's a gas in this case. Okay, so I've got my equation. I need to balance it. So let's go through 2 carbons. So I need 2 carbons. Okay, that's good. 6 hydrogens. Let's see, I need 3 hydrogens over there. So hydrogens, carbons are good. Now it's just the oxygen. So I got 2. I got, let's see, 4 hydrogens plus 3. That's 7 hydrogens. There's nothing that I can really multiply that by, which is kind of annoying. So let's go back and actually I should have kept the eraser up a little bit longer. Just double everything. That's the secret that we learned a little while back there. So double everything. So that's a 2. So that means I need 4 carbons on this side. 6 times 2, I need 12. So I need 6 hydrogens on this side. Now this should be a little bit easier to deal with. I've got a total of, let's see, 8 oxygens plus 6 oxygens. That's 14 oxygens. I can just throw a 7 in front of that, and then I'm good to go. Cool. All right, so I've got my complete balanced chemical reaction ready to go. Let's see. Question B. How many moles of oxygen are required to react with 0.8 moles, 10.8 moles of ethane? So 10.8 moles of ethane is what I've got, and I am looking for the moles of oxygen, so I'm just going to put those as a question mark. Now you might not want to write that out because there's like parts C and D and it gets kind of annoying, but this is what I mean by writing out the information that you have, the information that you're looking for underneath your chemical equation. Then it becomes very clear. So I'm just going to write the moles of oxygen are going to be equal to, we're going to start with the thing we know lots of information about. So 10.8 moles of C2H6. Nice. Now I want to multiply this by a conversion factor. And again, you can put that over 1 if you want to, but a conversion factor so that I get rid of moles of C2H6. Okay, nice. I want to end up with the moles of oxygen. So moles of oxygen. Cool. So those are going to cancel. Those are going to cancel. Now I just need to fill in the numbers. So let's see. It is 2 moles of my ethane for every 7 moles of my oxygen. When I go to plug this in, it's just 10.8 times 7 divided by 2. So plugging in all the numbers, that works out to be 37.8 moles of oxygen. Nice, that's not too bad. Put a box around that one. I think it's got sig digs. I think it's good to go. The next question is where it gets a tiny little bit trickier. So I'm going to erase a couple things. I might even use a different color here just because we're on to another question and we'll keep things. Yeah, that'll work. Okay, so the next one is how many grams of carbon dioxide would form if 0.550 moles of oxygen reacted? So 0.550 moles, and we're looking for, let's see, the mass of carbon dioxide. Mass is a question mark. Anytime we're dealing with mass, we can use molar mass to help us out. So carbon dioxide, that's 1 carbon, so 12.01, plus 2 oxygens, so 16 times 2. Now those are just the molar masses of the individual elements. So the molar mass, 44.01 grams per mole. Nice. Now we've got that all set up in front of us. We got all of the information that we have, all the information that we realistically need. So let's go ahead and let's start to think about this. My mass of CO2 is what I'm looking for. So I can go through and I can say, okay, well, I'm going to start with my 0.550 moles of oxygen. I'm going to go ahead and figure out the moles of carbon dioxide. Because if I have the moles of carbon dioxide and I have the molar mass, I can find the mass. So I got to cancel moles of oxygen, and I got to end up with moles of CO2. So if I'm canceling moles of oxygen, it's originally on the top. I got to put it in the bottom. Remember, you can always put a placeholder there too if you want. Things in the top cancel with things in the bottom. Cool. Now let's see. There's a 7 in front of the oxygen, and there's a 4 in front of the carbon dioxide. So there's my molar ratio. If I were to stop right now, I would have the moles of carbon dioxide. I don't think I'm quite ready to stop yet, though. We can do this in one big step. And if you're looking at the answer keys, remember the page numbers are a little bit messed up in those answer keys that I got online there, but the answers are all still there. The answers do them in multiple steps. I like doing them in one step. It's not that difficult. Forget about everything that we've got with numbers right now. Let's just focus on these units. So I want to end up with grams of carbon dioxide, and I have to get rid of moles of carbon dioxide. This is where my mole ratio comes in. It is 44.01 grams of carbon dioxide for every 1 mole of carbon dioxide. And then look what happens. Cancel, cancel. What are the only units that we have left? The only units at all? Well, it's just grams of carbon dioxide, which is exactly what we're looking for. So when I get out the calculator, I go 0.550. Let me clear it first, so it's the only thing up there, 0.550. I didn't even really need the 0, but that's okay. Times 4, divided by 7, and then times 44.01. I could do divided by 1, but that doesn't really change anything. So I hit enter, and this should be 13.8 grams of carbon dioxide. Awesome, nice. So all we're doing with this is canceling out units. That's it. We're using our balanced chemical reaction, equation, and we are canceling out units. Okay, let me just clean up what I've got underneath the reaction or the equation up top here, and we'll look at one more example. This is now a full-on example, part D. Excuse me, and we'll choose one more color. Let's see, what's a nice color for this one? Maybe we'll do that, whatever that one is. So now I've got a bit more information. So how many grams of ethane are needed? So that's my question. My mass is my question mark. To burn to cause 10.6 grams of water vapor. So let's see, 10.6 grams, that's my mass, of water vapor to form. Nice. Okay. Things that I'm going to need, because I'm looking at mass with both of those. The only way to get from mass to moles is molar mass. So my molar mass for water, 2 waters plus 1 oxygen, that's 18.02 grams per mole. Nice. And my molar mass for my ethane, that I need a calculator for. I have no clue, but I know that I have 2 carbons, so 2 times 12.01, and I know that I have 6 hydrogens, so 6 times 1.01. Let's see, that's 30.8 grams per mole for my ethane. Nice. Now I've got all the information I need. I just got to put it together so I get the grams of ethane. So let's just move that up so I'm not crouching down too low, and we can still see everything. So the mass of C2H6 is what I'm looking for. So I'm going to start off with the thing that I'm given a lot of information about, which is my water. So I'm given 10.6 grams of water. Now, in order to go and get the moles of something else, like in this case ethane, I need the moles of water. So I'm going to multiply this by a conversion factor so that I cancel out my grams of H2O. It was on the top, it needs to be in the bottom, and I want to end up with moles of H2O. Now I look at my conversion factor that I've got over there. It's my molar mass. It's 18.02 grams for every 1 mole. So 18.02 grams for every 1 mole, and then grams of water cancels with grams of water. If we were to stop right now, we would have moles of water. We're not stopping right now, though. All right, that's the only unit that's there. Let's focus just on that moles of water. You want to get rid of moles of water? It's currently on the top. Guess where you got to put it? On the bottom. We are looking for information about that ethane. I want the moles of ethane. So I'm going to put C2H6, my moles of ethane on the top. Now I look at my mole ratio. Let's see, it says 2 ethanes will react to produce 6 waters. And then the waters cancel. And that, again, that just comes from my mole ratio right up at the top of the screen here. 2 ethanes, and I'm circling it right now at the top, 6 waters. Cool. If we were to pump the brakes right now, the only unit that I would have left is moles of ethane. I don't really want moles of ethane. I want mass of ethane. So I want to cancel out moles. Moles are going to go on the bottom, C2H6. And I want to end up with the mass, so that's the grams of C2H6. Look what happens. Moles cancel with moles. Now I just got to go back to my mole ratio. It was 30.8 grams per mole. So that's 30.8 grams for every 1 mole. And the only unit that I have left here, the only unit is grams of C2H6, which is perfect. So let's just clear this up. I'm just going to plug everything in as I see it. So 10.6 divided by 1, don't need to do that. Let's see, times 1, I guess I don't really need to times by 1, and then divided by 18.02, then times 2 and divided by 6, then times 30.8. Excellent, hit enter. Turns out, kind of out of space, so I'm just going to write it below. Turns out that would be 6.04 grams of our ethane, C2H6. And I got kind of lazy there. I better put that it's a gas. Cool. So that's all there is. That's stoichiometry. It's all about canceling units. Now, I've done these sort of in bigger steps. If you want to do this in smaller steps, absolutely, it's no problem, but you can do it in one step. All you got to really focus on is canceling out units. Units on the top cancel with units on the bottom. Right? Grams cancel with grams, moles cancel with moles, as long as they're in the top. And also, please don't be lazy, right? If you don't write the little H2O or the C2H6 after, it can be very, very confusing which moles you're actually dealing with at which part of the question or the equation. Cool. So all we really did here, and I'm you know what? I'm even going to summarize this in one more color. Let's switch it to black. So this first step was to figure out the moles of water. And in order to figure out the moles, to go from the grams to the moles of water, we needed our molar mass. Our second step, which is essentially, there we go, right here, our second step, we figured out the moles of C2H6. So the moles of our unknown. And then finally, our third step is to figure out the grams of C2H6. Every question is going to be almost the same. Almost the same. And we saw it even in this example from B to C to D, we saw where we just kind of built up and we added a step every single time. So I think I'm going to leave that there. I know that there's other examples, so if you want to try out example 2 and example, example 3, 4. Answers are in brackets afterwards, at least for number 3 and 4. I don't think they are for number 2, but the answer is up on Google Classroom. So you can try those out as a bit of practice, and then when we flip the page over, holy mackerel, there's a lot of practice with lots of answers in brackets after the fact. I think there's like 12 or something like that. Here's what I want you to do with this. I want you to practice until you're comfortable with it, right? You don't need to do all 12 necessarily, but you need to practice until you're comfortable. So one last little recap. 1, you need a balanced chemical reaction. 2, write out everything that you know underneath the chemical reaction. It's going to help out an awful lot, right? Just keeping things visual. 3, you're going to be given enough information to find the moles of something. Find the moles of that. Let's see. Next step, find the moles of the thing that you're looking for, the compound that you're looking for. And then finally, last step, find the mass of the thing that you're looking for. That is a full-on chemical stoichiometric calculation. Not too bad. Anyways, I'm going to let you get to it. Please let me know if you need any help or anything, and we can absolutely go through. Answer keys are online. Just shoot me an email. Anyways, talk to you again soon, Chem 20s. Bye for now.